So this is session 5, which will be on generative adversarial networks, transformers, and new models. And the chair is Emma Wang from Cambridge. I'll pass over to you.
Okay. Let's start the oral session 5, generative adversarial network, transformer, and new models. I would like to invite the first speaker, Abdullah from the King's College London. He will talk about his research on a deep generative model of neonatal cortical surface development. Welcome.
Hello, I'm Abdullah. I'm going to be talking about deep generative modeling of neonatal cortical surface development. The first question is why cortical surfaces? The image shows that as you progressively become a more complex species, it's not just the brain size that changes, but the complexity of the brain. The brain undergoes significant folding and becomes a more complex structure. And we know that there's something there. And it's particularly worth studying because if you think about the brain itself, the cortex, it is a surface, right? It's frankly, it's just a folded sort of sausage. That's the shape, that's what your brain is. So it's quite important to remember that's the structure of the brain, and maybe that's the best way to model it. And it's particularly important in neonates. If the GIF is working, which it is, between around 28 weeks and 44 weeks, you can see from the GIF there's significant changes in folding and structure. And in the image, you can see these age template maps where you can see the changes in myelination of the brain. So it's not just the folding structure, it's also the changes in the cellular structure of the brain where the neurons are being myelinated. So there's a lot of changes going on at this period of time. And that's really the motivation behind the Developing Human Connectome project, with whom we are a part of, and we work with them to study this really, really important stage of neurodevelopment. We look at surfaces and volumes, but I'm the sort of surface team. And as you might imagine, there's clinical relevance here. If for whatever reason there is atypical neurodevelopment, then it's associated with poor cognitive outcomes, ADHD, autism spectral conditions, bipolar disorder, long-term learning difficulties. It's important clinically, and we know that this development process is affected by factors, preterm birth being the most significant. And there's something more to it, because when in the HCP, which is for adults, and the DHCP, when we take these images of the brain surface and we analyze them, we can predict some phenotypes. We can predict cognitive outcome. We can predict age phenotypes. We know that the information is there. So it's just a case of modeling it. And that's where geometric deep learning comes in, which is a very complex topic, which I'm condensing into one slide. But essentially, what geometric deep learning is about, it's about taking standard deep learning and applying it to domains that are irregular, a little bit weird. So the reason behind it is when you do your conv2D, conv3D, the mathematical definition of convolution actually doesn't suit surfaces, meshes, graphs, those domains. It's actually it actually doesn't work. The properties that make it so good on images and volumes make it not so great on the surface. And geometric deep learning basically proposes that, hey, you have to adapt that a little bit to match your domain. If you're a graph, you need a graph convolution. If you're a surface, you need a surface convolution, point cloud, mesh, whatever it is. We've done some prior work sort of benchmarking these methods, and we settled on a really good method that's from a model called Monet. So it's a surface-based convolution that it's based on Gaussians, and it works pretty well. And that is the sort of the convolution that we use in our network. We also, in terms of studying the brain mesh, we sphericalize it. We put it on the icosphere. Mathematically, we're in central mathematics. Yeah, mathematicians will have no problem with this, topologically equivalent surfaces. So you can do that. The reason that we do it is because icospheres have this very nice native up and down sampling procedure that's very computationally efficient, very easy to do. I can upsample to a gazillion vertices and drop all the way back down to icosphere 1, which is 12. And the reason you want to do this is, again, when you're in the nice images and volume space, when you do your downsampling, your max pool, your striding, whatever it is you want to do, you go from a grid to another grid. But if you have a surface that's a little bit weird, you have, you know, something like this, it changes the neighborhood of different points, it changes the global structure, and then it gets very difficult to define filters consistently if all of the neighborhoods are changing depending on how you downsample. And that can be difficult too, and that's why the icosphere is so powerful and why it's so commonly used for surface analysis. In terms of how it goes into like actual models, networks, it's kind of the same thing. So here we're doing a cycle GAN, so we have generators and discriminators. So how do I build a geometric deep learning convolutional network? Ooh, it's actually quite easy. You just replace the up and down sampling with the icospheric. You take out your convolution, that the normal 2D or 3D one, and you put in the monad in our case, and that's it. I do a nice little thing because I'm looking at development. So I like to output a difference map, and it's very easy to just add it and then get your new prediction. It's quite helpful for clinicians as well to see difference maps. We'll see that later, actually. It's quite a nice result. And cycle GAN experiments are what we're doing. This is quite a well-established sort of framework where you are able to switch between different domains, dog, cat, horse, zebra, male, female, MRI to PET scan. It's quite widely used. And in our case, we're using it for switching between a low scan age to a high scan age, where we define low and high as less than or more than 37 weeks. And then in the second experiment, low early birth, really preterm birth, less than 37 weeks, to more than 37 weeks, which is term birth. And the data cohort kind of shows this, right? You can see that we have two different ages. We have a age at birth, right, which is when the baby's born, and we have an age at scan. And this is a post-menstrual age at scan, so it's independent of the time that you're born, right? And you can see from this, there's kind of two trends here, and those are our two experiments. One is the sort of Y equals X that we're looking at. That's the scan age. So the babies are born and then essentially scanned sometime after birth, quite soon after. And the birth age cohort is, hey, we got a bunch of babies vaguely scanned around the same time, but they're born at different times. And in both cases, we're trying to, our cycle GAN is turning from the blue, which is the blue set of points, to the orange set of points. And immediately you can already see one issue with this, which is there are loads of blue and orange points that are quite close together, closer than, you know, the rest of their set. So why are they two separate domains? And that's kind of a limitation of our work, that we've sort of taken this continuous age and we put a 37-week boundary and split them into two, when you could say, hey, 36 and 38, they're not that far away. That's a valid point. It's more clinically motivated for birth age because we doctors define 37 weeks as term and preterm, but you can still make that same claim. So we'll see that come up in a moment. In terms of our qualitative results, we're actually quite lucky. We have longitudinal data. So we have babies born, scanned, and then scanned again later on. So hey, if I have a cycle GAN that's aging this baby, I'll compare the later scan to my predicted aged sort of output. We can see this for two subjects. It gives actually pretty decent results. It gives the kind of changes in myelination that we expect. So on the far left is the input and the far right is the output. We can see this ground truth is quite close. There is a problem here that we have no power, no control over the degree of aging. That's one little issue. Nonetheless, there's some things we want to consider here. How can we quantify the quality of our predictions? You know, images are nice, but we want some numbers. The second thing is myelination is not very subject specific. It is a little bit, but they all vaguely look the same. But for curvature is very, very, like folding pattern is very subject specific. So if you look at the curvature, we can really see if we're predicting something real or we just learned the templates. And curvature is quite involved, so I won't dwell too much. But if you look at the third column, you can see that our predictions are quite different. They represent, you can see the cursor, right? So if you see here, this is a good example where this sulca is split in two for that particular subject, but it's more like one on the other subject. And around here as well, you have quite a different structure compared to this subject. And if you look at the original ones, the output reflects the original. It is quite, it reflects the subject specificity, which is what we're looking for to really validate. We're learning, we're making predictions on the subject, not learned vaguely what happens to myelination, which is important for clinical application. And we also have, we can also see that it's learned some of the things that we expect for aging and curvature. We have sort of increased folding sort of in the lower temporal lobe. If you look at the red circle, we have a really nice result where, which is why curvature is very difficult to predict how it's going to change, frankly, just in general. And there tends to be loads of changes in topology. A lot of one long sulci might split into two. And what's quite nice is that the models predicted that in the red circles. You can see that there's a change in topology. It's split into two, and we correctly predicted that, which is quite nice. Quantitatively, one way to quantify our results is to say, hey, if we have an aged scan, it should be closer to the later scan than the input, right? That makes sense. So if we use an image similarity metric such as a PSNR, we can check the closeness of the original, the input and the later scan, and see if our output is closer to the age scan than what we started off with. We should get better results than what we started off with. That's otherwise there's no point. And if you see this box plot, you can see image similarity on the y-axis and the relevant metrics modalities on the x-axis. You can see on average, yeah, we do get an improvement, but we can go a little bit deeper here and look at individual subjects. So here, this graph actually puts the age of that ground truth later scan on the x-axis. So all of the green lines, it's a lot of information. All the green lines mean we've got an improved result. It's great. But the red lines show subjects in the test set where actually our scan is actually worse, quote unquote, worse than what we started off with. And we can see there tends to be a big cluster down at the lower scan age. And when we look at that, this failed example, we can see it's actually maybe more complicated than that. So in this case, we have a subject born very early, 28 weeks, 9 weeks premature, and its 38-week scan is there. It's actually very lacking in myelin. You'll see why in a moment, it's because it's quite premature. And our prediction is it's probably just a lot more than 38 weeks. It's probably not the case that we've the models failed. It's just that we predicted so much further than the difference between what we started off with and the time of scan. And that probably reflects why our results are a little worse for the earlier second scans, because we're predicting so far ahead. Well, that's the argument. The other argument is it could be model failure. I'm not so sure because, you know, it is predicting what we expect in the development of myelination. So it seems a different age hypothesis is correct. I actually like this because if we were able to produce age-specific output, so if I could guarantee you that the third image was at 38 weeks, then actually the difference between these two scans is not a failure. It's actually a measure of how premature the baby is, how affected the baby is, because it's actually not to blame the subject, but you know, they're very premature and the subjects that I looked at were not. So it's deviated from what is being predicted. And that's actually a measure of how its neurodevelopment has been affected. So this actually could be a practical, of practical use if we could get age-specific predictions. And my favorite results are on the birth age experiments, where we don't have longitudinal data. You can't be born, scanned, and born later and scanned again. So Instead, we just say, hey, let's see what happens. Let's take a term baby. We're going to take this term baby and we're going to make it into a premature version of itself. And we're going to look at the difference maps. What happened? Preterms have decreased myelination. So that's why that previous subject, which was born 9 weeks early, looked like he didn't have any myelin, because we know, and this is in existing research as well as the model prediction, that myelination is decreased in preterms. And my favorite result is on curvature. So again, it's predicted that curvature has gone up, but if you really take a good look, you can see that there are patterns where the myelination, the curvature is not changed very much. And if you follow the patterns over to the subject, those are the sulci. So it's predicting an increase in curvature, but it's predicting an increase in gyral curvature, which is the bumps instead of the chops. And that's exactly what you get in other research and all these analysis and medical research and all this other wealth of evidence has always said, oh, there seems to be an increase in gyral curvature, which is amazing because my model has predicted the same thing, which I love that. We can also quantify our results, right? So you could train a classifier. You could say, hey, preterm term, classify them for me. And see if our fake preterms and terms fool this classifier that's been independently trained. So our classifier has a 94% accuracy, but on my fake data, it's fooled 78% of the time, and 100% of the time the confidence is dropped because it's not quite been fooled, but almost. And yeah, so the conclusions are that the CycleGAN model is a model of aging. Its predictions are realistic, they are subject specific, and it's managed to identify differences in line with existing research. It's very nice. The problem is the whole control over aging thing, you know, discretizing this age space, not being able to control how much you age, binning these things. This is like the key, like sort of focus of further work that would take this sort of a project to the next level. And that's what we're working on now. Thank you for listening. And
thank you for your interesting presentation. Any questions from the audience?
Hi. So if I've understood correctly, yeah, you've made a model that retrospectively can look at whether a child was what's the word? Smaller than what the model's predicting.
yeah, it keeps the scan age the same, but puts the moment of aging back. Oh, do you mean the birth age or the scan age experiments?
The ones that you shown just last.
All right, so that's the birth age. So it
Yeah.
keep the scan age the same, but the point of the birth is gone further back.
Okay. Could you look at whether if you had like the first scan, whether you can predict whether how they're gonna be preterm or not?
If they were preterm. So you'll have to speak. I'm a bit bad of hearing, so
No, it's okay. I think I'm just confused. We can chat about it later.
yeah, you can ask me whatever you want at any point in time. Don't worry.
Okay, the time is up. A quick question. Very quick question.
Thank you very much for a really nice talk. So I have a couple of quick questions. First of all, when you map to the isosphere, how do you do that mapping? And do you take into account the geodesic distances and the folds and so on? And how do you unfold those? And my second question is, your GANs, really nice results here, but do you think that the GANs that have learned from, you know, the various birth ages, that data may have influenced what you're producing here?
Oh, the variation in scan age, is that what you?
Yeah.
Yeah, I mean, it is like, I think I didn't control for the scan age, but I think when you look at the actual images, you see that it's not changing the things that we expect to be changed in scan age. It's kept it's kept, like, for example, the curvature, it's not changed the structure, the folding structure. It's just changed the sort of the curvature levels of the folding structure. And so I mean, that's an argument I haven't conditioned on scan age. You could certainly make that that point. Yeah. I would just argue that from the cortical folding patterns not having, if we know what the changes look like when you change the age at scan, we know that there are changes in we don't see here. We don't see the changes in scan age, at least in the curvature results. We don't see what we expect to be changes in curvature with respect to this change in scan age, but we see changes that are reflected in the literature in birth age. Yeah, I mean, you're still right in that is another the opposite side to the fact that we weren't able to condition for age. We aren't able to control for it. But I still think I'm a bit confident to say that based on the actual output, since it left the folding pattern alone, that means that it's not aging the baby, it's changing the birth age. And in terms of map to icosphere, it's barycentric integration.
Okay, thank you very much for your nice talk and answering. Let's move forward to the next speaker. Thank you very much. Then let's move to the next speaker from UCSP, who will talk about the polyp tooth set, improve the polyp segmentation with vision transformer. Welcome. He should be on Zoom.
Hello, everyone. Do you hear us? Do you see our screen?
Yes, yes, we can hear.
Okay, great. Just 1 second, please. I will just have to put here on the phone slideshow. Do you still see it?
Yes.
Hello?
Yes.
Okay. Great, great. Thanks a lot. So my name is Javier Montoya, and this is a joint work with Mr. Vittorino Mandujano. This work has been conducted at the University of San Pablo in Arequipa, Peru, and at the University of Applied Science in Lucerne. Our work is entitled Polyp to Seg, Improve Polyp Segmentation with Vision Transformers. Our work focuses on cancer analysis. Cancer is the second leading cause of death worldwide, according to the World Health Organization. And actually, polyp or colorectal cancer is the third cause of death in men and the second cause of death in women. The amount of cancer patients is expected to almost be doubled in the next 20 years. One important thing is that if cancer is early detected, about 30 to 50% of the cases can be prevented. And this is the case of colorectal cancer, in which by early detecting polyp, we can avoid this type of cancer. The goal here is, given a colonoscopy image, which is an RGB image, we have to divide it into a set of coherent semantic regions, like the ones here on the right. So actually here on yellow, we see the annotated polyps made by the specialist. Some of the challenges that we found in this type of images are related, on the one hand, due to the acquisition factors such as illumination artifacts. So here we see some reflections given by the camera projected on the tissue. We see some other problems of occlusion, clutter, and as well large interclass variability. We see that the size of the polyps, they change, and we have as well other artifacts which are related to the anonymization process, like for instance here, the name of the patient, or as well the date when the images were acquired. The state of the art in polyp segmentation can be divided into three major groups. The first one are the so-called handcrafted approaches, in which traditional approaches use texture or color information combined with geometrical properties to delineate or to extract these polyps. The problem with these approaches are that some parameters have to be manually tuned up, and the errors which are found in one stage are projected along the different stages of the pipeline. The second group of approaches are based on convolutional neural networks, which are basically trained end-to-end, and we can obtain this hierarchical representation. And the more recent approaches, generally speaking, in medical segmentation are these hybrid approaches in which transformers and CNNs are used to obtain a finer segmentation. And actually, this is where our approach lies. We are proposing here a hybrid approach which uses transformers for long-range spatial delineation and CNNs for localized pixel-wise relationship information. So the major three contributions of our work are as follows. We propose a novel coarse-to-fine model for polyp segmentation from colonoscopy images. The second contribution of our approach is some novel modules which are proposed focusing on the multi-scale aggregation of semantic segmentation, and we propose a new approach which performs better than some of the state-of-the-art approaches. So this is an overview of our proposed method. Our proposed method has five major components. We have first a multi-scale feature extraction mechanism, which is based on a transformer encoder in order to capture this long-range spatial information. We have a second module to reduce the number of features and thus to reduce the complexity of our model. We have a third component in which we aggregate directly feature scales, and then we have this deep supervision approach in order to obtain a better refined polyp segment result. So we are going to go step by step over the different components of our proposed approach. The first one is our encoder, which is based on this pyramid vision transformer. We use it as an encoder, and this transformer has the benefit that it extracts a set of multi-scale features by using a pyramid decomposition of the input image, and this approach can be used for dense prediction tasks. For more details, you can please have a look at the original publication. So one of the things of this encoder is that based on the depth or on the stage we are at the encoder, we have a different amount of feature maps. So for instance, in the highest resolution, we have 64 feature maps, and in highest or let's say low resolution, we have 512 features, which gives at each scale a different amount of feature maps and give us different complexities. So what we do at the next stage is we reduce the number of features to 64 by using this compression module, which is composed by a convolution layer by using 1x1 kernels, followed by batch normalization and ReLUs. This gives us the fact that all the stages have now the same amount of features, and therefore they have the same relevance regardless of the different stage where we are. And as well, it helps us to reduce the number of parameters of our model. So once we have a uniform amount of features at each of the stages, the question is how can we combine the information from the different stages into one single module. And therefore, we propose here this novel module, which is called the feature aggregation module, and it combines directly features from direct neighboring scales. So basically here we have the higher features coming from the previous stage, we have the lower features from the current stage, and what we do is after using these sort of modules, which are based on convolutional layers of 1x1, batch normalization, and the silo activation layer, we multiply each of the features, and then we apply, following the principle of a mobile net, a set of depth-wise dilated convolutions, which are concatenated. Then we apply a convolutional layer followed by a batch normalization, and we sum the original feature in a sort of residual connection, and then we apply a SILU. So basically, the effect of this novel module is that we are aggregating features from different scales, we are aggregating attention mechanism, and at the same time, we are characterizing the different sizes of the polyps. As we have seen at the previous slides, is that the size of the polyps, they can vary along the different images, and therefore it's important to capture all this local information. And that's why we decided here to use on parallel different dilated convolution factors. And remember that they are applying sort of depth-wise separable convolution to reduce the number of factors. And those are here some of the trained features. Given an input image, you see here that at this scale, which is the lowest resolution scale, this FAM3, which stands for Feature Aggregation Module at stage 3, we already see some part of this polyp. And as we go through the higher layers, we then see more the structure or more fine details about the structure of our polyps. Another component is another novel module, which is this context attention mechanism. And basically, the medical literature has shown us that usually it's important to characterize the color and as well the texture information of the polyps. And if we have on the top of our heads the hierarchical representation of the features, we know that the first layers and the filters that are learned correspond to the texture or color information. And that's why we apply only this module at this top level. We have conducted experiments and we're as well analyzing what's the effect of using this module across the different stages, but we gain the benefits only by applying at this stage. So basically, this multi-context attention model has as input a set of feature maps, which are coming here from this arrow below, from this first stage. And then we apply as well some kernels on parallel, which are multiplied with the original features and combined together with this concatenation approach. So what's the effect? If we have a look here at our input image and at the learned features, we see that all the regions that were belonging, for instance, to some noise artifacts, such as these reflection artifacts, they are gone. So we highlight basically the features that are related to the polyps or to the tissues itself, while we remove some noise artifacts. And this is done by using this min or max operations along the different feature channels right at the beginning of this module. And finally, in order to characterize the different sizes of our module, we use this deep supervision approach by not only applying it on each stage separately, but we add a sort of virtual outputs in which directly combine neighboring outputs. So we combine AUX4 with AUX3, create another output, and we do it over the different outputs of the model. In order to validate our approach, we use 5 data sets, and we follow the same protocol proposed by an approach which was published last year at MICAI, which is called PRANET. And here we are illustrating only 2 of the data sets because of time constraints. The first one is the clinic CVC data set, which has been acquired at the University Hospital in Barcelona, Spain. Here there are about 620 images which were annotated manually by clinicians. The images are of 400 times almost 300 pixels, and this data set was published in the year 2015. Another recent data set was acquired in Norway at the VV Health Trust, and here we have 1,000 images which were manually annotated by clinicians, and see here that the size of these images, they varies. This data set was published in year 2020. So in this evaluation protocol, part of the images coming from the clinic CVC and the CAVA-CIRSEC data set were used for training, and the rest of the images together with these 3 other data sets are used for testing purposes. In order to validate our approach, we use as well a set of standard metrics such as the DICE score, intersection over union, MIP, mean absolute error, or weighted F measure. And those are some of the results that we have here only for the Cavasier segmentation data set. Again, in the paper, you have a more detailed overview over the statistics over different data sets. So what we see here is we compare our approach with about 10 different models. The models that you see here highlighted in orange are more general segmentation approaches, such as the fully convolutional networks. We have units, attention units, and unit plus plus. And here in green, you see more, let's say, specialized architectures targeting polyp segmentation. And here on the different columns, you see the different results. The higher, or if you see an arrow pointing upwards, you see that the higher the values are better. And here for the mild, the lower values, the better. And what we see here in blue is that our model is able to outperform most of these approaches, being the second one, this polyp PBT, which has as well a hybrid approach, which use as its encoder the pyramid vision transformer, and it has as well a combination with CNS and graph neural networks. So our approach is almost improving the state of the art by 0.8 points in terms of the dice score, almost as well the same amount in the intersection over union, and you see as well here the case of the different metrics. So what about the number of parameters and the dice score? So in these plots, what you see here in the x-axis are the number of million of parameters. And here on the y-axis, you see the mean dice score for the two data sets that we have, that we are showing now. Again, in the paper, you will see more results. And what we see here, that our model almost is on average, or let's say has the half of amount of parameters compared to other approaches, and we are able here to outperform the other approaches in terms of the mean dice score. What about the qualitative results? Here we see some images, some illustrative images. On the first column, we see some images from the CVC clinic dataset. On the second column, we see the ground truths, which are these manual annotations by the doctors. In yellow, we see the masks, which are related to the ground truths, sorry, to the true positives. In red, we see the false detections, and in blue, we see the misdetections. The third column are related to our approach. And here on the last three columns, you see the top 3 results from different approaches. And what we see here is that our results are more close to the true positives. In the case, for instance, of DCRNet or PRANET, we see some false detections. However, most of the approaches fail still in detecting polyps that are really small in size. And here we have more qualitative results for this Cavasier segmentation dataset. Again, we see here on the first column, the input images, the second column, the ground truths, the third column, our results. And we see here in the last 5 columns, the results from some of the state-of-the-art approaches. We can see here that our approach is more in line with the annotations from the doctors. This data set is challenging because you see here some artifacts which are related to the anonymization procedures after acquisition. We see as well some noise artifacts related to the date or acquisition date of the images. We have as well some spectral or illumination condition artifacts, which are still challenging in almost all of the approaches. You see again here, these false negatives along the different approaches. We are able to cover more about these regions, and this is based because of our a priori module, which is this multi-attention context module in which we compensate the noise artifacts. And then to summarize our work and to talk about the future work, first of all, we have conducted extensive results on 5 challenging data sets. Again, for the time constraints, we have only presented here results on 2 data sets. Our model reduces the number of parameters compared to some of the state-of-the-art and still is able to outperform them by improving the results in terms of mean dice scores or different metrics. And it uses this a priori knowledge in which we try to remove noise and focus on the texture and color information, and as well, we are able to obtain or combine features directly from different stages using attention mechanism to reduce the number of false positives. What we would like to do as feature work is to add more precise prior knowledge, for instance, to characterize the contour information of these polyps by exploring contour losses. And we believe that if we try to combine some sort of depth information, we can as well reduce the false positives and the false negatives. And we would like well to explore the possibility of using other type of data sets, such as video data sets, in order to have more training samples and to see whether we achieve online results. So this is it from our side. And thanks a lot for your attention. And we are greeting you from South America.
Thank you very much.
Are there any questions? And by the way, Vitorino is also online here.
Any questions from the audience?
So thank you for the nice talk. I think it's a very interesting step in the right direction. Do you have specific on the difficult flat polyps? Because the flat polyps, I guess, is the most challenging for the doctors, for the physicians. They are missing them more than the others. Do you have some hints at this point?
Yeah, I think this goes in line with our feature work, in which we should try somehow to use this depth information combined with the contour information. And we believe that by combining these depth cues together with the contour losses, we are able to better detect the flat polyps, in which basically you cannot almost differentiate whether they are polyps or regular tissues. Do you have any other answer, Vitorino? Do you want to say something related to that question?
Yes, I would like to add some information. If you can show me the picture of the architecture in page 10. All right, thank you so much. Some of the blocks shows in the method, some of them has been inspired in other blocks of camouflage, like MCAM. The MCAM is perhaps the cause of why is in many cases able to recognize and distinguish the reflection of the segmentation.
Okay, thanks. Any further questions?
Hey, thank you for the great talk. So I've got a question. You got really good results in comparison to other state-of-the-arts. So I wonder if you have checked the generalizability of your method by doing cross data set validation. So training a model on data set A and then testing on data set B to see how it performs.
So when we publish here the results, we have only published part of them, but we have done those experiments, and this protocol goes more or less in line with what you have posed. Like, for instance, these three data sets, CVC 300, ColumnDB, and ETIS, they have not been used at all during training. They have been used only during testing. And as well, on parallel, we have performed like one-to-all data sets, like training one data set and evaluating the rest. And we see the same behavior in which our approach is able to obtain a bit more of points in the statistics. But directly, if you have a look at the paper and the statistics of these three data sets, they have been not used for training, but directly for testing. And we see, again, the same behavior.
Yeah.
Okay, thank you very much for your answering. Let's thank the speaker again.
Thanks a lot for your patience and your time.
Thank you, sir. Thank you very much.
Okay. Let's invite the next speaker, Michael, who's from University of Cambridge. His talk will be from astronomy to histology, adapting the bell worker algorithm to deep nuclear instance segmentation. Welcome.
Hello, everyone. My name is Michael Young. As a disclaimer, I'm actually a doctor rather than any technical person. But that being said, my presentation is about how and why we applied this algorithm developed in astronomy to solving a task related to computational pathology. So let's start by just giving you a brief sort of overlook of what we're trying to do. So if we take a normal cancer pathway, you have a patient, they present, this could be at a GP, this could be an A&E, this could also just be incidentally via scan done as an inpatient. And then maybe they'll have some further investigations, maybe a referral to secondary center. And somewhere down the line, they're most likely to require a biopsy because a biopsy is the gold standard for a diagnosis of cancer. Now, if we zoom into the biopsy process, just to give you a brief outline, biopsy is where you take a tissue sample and then a pathologist will look under a microscope and make their diagnosis. The role of AI in all of this is how you can have the AI, for example, as a second reader, and then they can check the results and compare against what the pathologist says. More specifically, we can use segmentation models, which can then give us information about the tissue architecture, the cellular and nuclear morphologies, and then input that into features used for a classification model. Now, I've mentioned segmentation, classification. Let me just give you a definition of what all of this means. So by classification, we mean a one prediction per image, like this, for example, would be a cat. Semantic segmentation is where you give a prediction for every single pixel of an image. You can also have localization, where you draw a bounding box around the classified object. You can also have object detection, where you draw bounding boxes around all the objects that you're looking for. And then finally, there's instance segmentation. And this is what I think is the most difficult out of all of these tasks, which is where you not only generate a prediction for each pixel about what class it belongs to, but also what instance of each class it belongs to. And you can have very analogous stuff in computational pathology. Now, focusing on instance segmentation, there's really two main methods used today, and they're the top-down and the bottom-up methods. The top-down methods, they apply object detection first, followed by segmentation. And the bottom-up methods, they perform the segmentation first, and then use some sort of clustering to pick out the different instances of the segmented objects. So probably the most canonical and definitely the most influential method, which is a top-down method, is the masked RCNN. Let me just give you a brief cliff notes of what this actually means. So the masked RCNN, it takes in an input image and it generates, extracts lots of features and then uses these features to essentially predict many, many different bounding boxes of where it thinks the objects are. Now, the issue is you might not have one bounding box per image, so you need to suppress some of them. And that's what we refer to as the non-maximal suppression. But that's the job of the region proposal network. Once we've got our candidate bounding boxes and we suppress the ones we don't want, we need to align them with the image. And the role of that is this ROI align section of the model. And the important thing with this part is that the bounding boxes, they're not guaranteed to be integers. They're most likely to be sort of decimal points. And so you need to do a bit of interpolation to make sure they actually fit the correct section of the image. And then finally, once you've got your bounding boxes and you've sort of cropped into the objects that you're looking for, you can perform some simple segmentation to generate the final instance mask that we want. Now, conversely, there's the bottom-up methods. Probably one of the simplest and definitely one of the most commonly used bottom-up method is the UNet and watershed. So I'm afraid I don't have much time to talk about what the watershed algorithm, how it works, but there's really sort of two things you need. what you need is you need to know where the background is. And for that, you can just do a simple binary segmentation task as above. And you also need some markers to say where you think all the different objects are. And we generate that using a distance map. Now, let me just talk about the distance map for a second. So imagine we have this image over here, and this is its corresponding label. What a distance map is essentially for each pixel, you're saying, how close is it to a boundary? And we give it a value based on that distance. And for here, this is the Euclidean distance. And we say, the further you are from the boundary, for example, the boundary of a nuclei, the higher your pixel intensity. Now, you would be forgiven if you thought this was also a distance map. And in fact, this is actually images from astronomy, some stars looking at molecular clouds. Now, the whole inspiration of this project is actually noticing how similar distance maps are from these molecular clouds. Let me explain. So I think if there's one thing to take away from this session is to know what fell walking is. I mean, I've lived in the UK for 24 years and I've never heard of the word. Essentially, fell walking is a hobby where you hike up mountains or hills. Why is that relevant? Well, if we take our input image, let's say we take the molecular clouds. And if we project that image onto a plane and we say the distance above the plane is based on how high the pixel intensity is, well, the first thing that's obvious is this looks like a bunch of hills. Now, that intuition is the whole intuition behind the Fell-Walker algorithm. Let me just give you a brief summary of what it's trying to do. So what you do is you pick different locations randomly across the image, and you say, let me look around my neighbors, and let me pick the next pixel, which has the highest difference in value from my one, and let me jump to that neighbor. As you iteratively complete this process, you end up climbing uphill to a local maximum. All the pixels which converge onto the same local maximum are therefore classified as the same instance, which then leads us to this nice final instance segmentation mask that we generate. So how did we use this algorithm into our models for solving a computational pathology task? Well, we used a dual UNet, and we essentially, again, need the same things that the watershed algorithm I mentioned before needed. It needs a distance map, and it needs a binary segmentation map as well. And with these two pieces of information extracted via a deep learning model, we can put these into the Fell-Walker algorithm, which will then give us the final instance segmentation mask. So you know a data set is pretty important when you've seen it yesterday as well. This is the Conic 2022 data set, and it's essentially the biggest instance segmentation data set we have at the moment in computational histopathology, which has over 500,000 nuclei. So let me just say a brief word about the evaluation metrics. There's really a big difference between semantic and instance segmentation, but it all boils down to one problem. Whilst in semantic segmentation, you know in advance how many classes there are. In instance segmentation, your model doesn't know in advance how many objects are in the image. And that one seemingly small difference actually leads to quite a big problem when you're trying to evaluate it. So on the left, you see the dice score classically used for semantic segmentation. On the right, you see this seemingly ugly version of the dice score. It's doing almost the same thing. The only difference is you need to start matching the different instances to the ground truth. There's also the F1 score, which in this case we use for detection. And then there's the Jacquard index equivalent used for instance segmentation, again, needing some extra matching to make sure we can evaluate instance masks. So let me just show you some results from our experiments. So what we can see is the three different metrics plotted on a graph. The x-axis is the percentage of data that we used. So we were interested to see how does our model perform across varying amounts of data used. So all the way from 1% of the data, which is about 40 images, all the way up to 100% of the data, which is about 5,000 images. So what you can see is obviously the performance improves across all of the algorithms, but the Fell-Walker algorithm does consistently better across all different data sizes. So let me give you some qualitative comparisons to make as well. So let's just zoom in on just two key parts. So look at this is images from 1% of the data at the top and 100% of the data at the bottom. There's really, I think, two key insights I want to point out, and really part of the motivation behind this project as well. So if you look in the middle at the top at the watershed algorithms output, you can see the borders are not very satisfactorily segmented. In fact, they're always under-segmented. And this actually stays even when you use 100% of the data. So this isn't a problem to do with the data. It's a problem to do with the algorithm itself. Now, the Fell-Walker is actually a type of watershed algorithm, and it doesn't suffer from the same problem. And the reason is because it inverts the idea of the watershed. Rather than sort of flowing down the hills looking for the where two different peaks converge, you're actually going up the hill. And that one subtle difference actually gives rise to such a stark difference in qualitative comparisons as well. And then the second point I want to make is if you look at the mask RCNN, probably one issue of the mask RCNN is that it relies on axis-aligned bounding boxes. And this can give you some real problems when you're working with very, very little data. And also when the nuclei are all in different orientations that can then lead to overlaps that you don't really want. So the final thing we did was, we used the dual unit as our backbone, but that's not the only one we can use. This is a very flexible method, as with all bottom-up methods. And so we tried different architectures. The one comparison I want to point out is, if you remember earlier, we saw the mask RCNN versus the Fell-Walker, and we saw the F1 scores very similar. But actually, if you look in terms of the parameters, this is a mask RCNN trained with a ResNet 50 backbone. It's got an order of magnitude more parameters than the simple UNet and Fell-Walker we used. And yet we have very similar results, if not better, with Fell-Walker. So let me just give you some conclusions about our work. But let me actually just point out what's the whole point of this. Well, as we're doing segmentation, the whole point of it is to then use it in a clinically relevant situation. And to do that, you need to develop very strong baselines to compare your work against. The Neonatal watershed is used as a very common baseline. But as we can see, there are some systematic issues, especially with medical data, where the intensity values between objects are not often clear. And so the model we propose is hopefully a better baseline that can be used, especially for medical images, to then compare against other methods that hopefully will be developed in the future. Thank you very much.
Thank you very much, Michael, for your fantastic presentation. Since the time is up, we only have one quick question, right? Okay.
Thank you very much for a really nice talk. My question is about the performance of this algorithm, particularly on tumor nuclei, which usually have high chromatin texture, not really uniform in their intensity. Have you seen how it performs as compared to some of the other algorithms, particularly for tumor nuclei?
So very good question. So I think I've got 2 points. Firstly, no, we haven't, but I think we can expect it to do quite well. And the reason we can expect it to do quite well is fundamentally to do with how the algorithm works and why it's different to the watershed. Because as I said, the watershed, it relies on pixel intensity values, which would be an issue for tumor nuclei. But the Fell-Walker, the only information it actually does is it uses the distance map, which is actually very different to looking at the actual pixel intensities. So you can sort of circumvent the problem by actually ignoring the sort of challenging pixel intensities that could be misleading the algorithm, and instead focusing on more important data that's got less noise and can hopefully give us better segmentations. Thank you very much.
Okay, thank you. Then we will end this oral session. Let's thank all the speakers again.
So next, we will welcome our keynote speaker, Professor Alex Franzi. And while Alex is setting up, so I will give some brief introduction for him. Well, okay, so let's welcome Professor Alex Franzi. So just a brief introduction for him. Professor Franzi is a Diamond Jubilee Chair in Computational Medicine at the University of Leeds, with joint appointments at the School of Computing and the School of Medicine. So he's also Royal Academy of Engineering Chair in Emerging Technologies, focusing on precision computational medicine for in silico trials of medical devices. And Professor Franzi's main research interest lies at crossroad of medical image analysis and modeling, emphasizing machine learning and computational physiology. He has a particular research interest in statistical models applies to populational imaging and in silico clinical trials. And he has been the principal investigator and all scientific coordinators for many like national and international projects funded by public and private sets, totaling over 50 million pounds. And Professor Franzi edited like several books and editorial articles and over 260 journal papers in leading international journals in his research fields. And he has been guest editor for many special issues in the major medical image analysis journals. And he's also chairing several of these medical imaging analysis conferences internationally, for example, ISPI, BCI, and others. And I'm sure Alex will introduce you the ISPI conference next year soon. To recognize his success in research and leadership, Professor Franzi has also been elected as IEEE Fellow, SPIE Fellow, BCI Fellow, and also he's also a Turing Fellow as well. Okay, hand over to Alex.
Thank you very much, Juan. So thanks a lot. Thanks a lot, Juan and Carola and Angelica as well for the invitation. And what I'd like to do today is give a perspective about how imaging can be used for something which is a bit outside imaging, and in that sense, help to stimulate a bit the thinking about the impact that the community can have as well in other areas, but also the importance of working not only with other disciplines in, let's say, medicine and biology, but also with other engineering disciplines and mathematics and computer science. So I'd like to start first a bit, what is the story behind the story of everything that I'm trying to do? Even if it may sound a bit eclectic, there is a logic behind that. And this is work that we've been, and ideas that we've been developing over the last 20 years, but particularly over the last 10 or so, in collaboration with other academics from Leeds that we worked together before in Sheffield. So the first thing is, when we try to do developments in medicine, most of the time what we need is two things. We need to have information about the particular position of a patient, let's say all the properties, the phenotype, but also an understanding of the disease. And this is, if you think in terms of a sat-nav, is not only important to be able to do very good measurements of a patient's position, which is kind of the GPS coordinates, but you also need to have the map, which is a quantitative understanding of the disease in itself, so that you actually can position and think about what would be the situation if you have your perfect coordinates in GPS, but no map, or a great map, but you don't have a clue where you are, right? And I think we need these two areas. And to do that, I think computational medicine, what it's trying to bring is inputs from mathematics, from engineering, and from physics, from computer science to actually better understand disease. But we want to understand it at two levels. At the levels of individuals, and a lot of the algorithms that we develop, we try to show precision and accuracy and how good we do in a particular subject. But it's also important that we are able to deploy those algorithms really at a larger scale. And that is a different types of accuracy, because it's about how many times you fail when you run these on several tens of thousand cases, for instance. So questions that I'm trying to address by combining all of these ideas is basically what constitutes disease, what constitutes normality in the first place, how we quantify that, and also, can we optimize specific therapies to make the therapy more personalized and more effective for a particular individual. So this is something we've been working over a number of years, and we tend to call it precision imaging, which is the idea that imaging needs to be, or image analytics needs to be both descriptive. It also needs to be able to be predictive, and also allow you to do integration of information. And by integration, I mean beyond, hopefully you will see examples throughout the talk, but it's beyond just registration. By predictive, we mean beyond just being able to do a regression. And by descriptive, we mean more than just be able to do statistics on certain phenotypes or biomarkers. Fundamentally, what we have otherwise to deal in this current day and age where we are overwhelmed with data is to transition from access to data, which we have in abundance, to actually be able to have access to wisdom or validated knowledge, which essentially is, ways to actually interpret the information that we have, and information is a structured data in the first place. So there is a transition from going to data to wisdom, and only when we are there, we actually can take decisions, which is what clinicians really care about. And I contend that there are two ways to do that, at least one, which is what we could call today AI or deep learning or machine learning, which is a phenomenological bottom-up approach. You have no understanding on the mechanisms, but you have lots of data, and that's great when you're in that situation. But ultimately, you want to understand, and that's why we talk about explainable AI and a lot of other things. But also there are some times where we do have a good understanding on the physics or the mechanisms of the biology or physiology in place. And it would be a waste to actually not use those priors and somehow utilize them to interpret the data that you collect. So those is what we call mechanistic or top-down approaches. And in reality, it's never one or the other, it's a combination of both, and you have middle-out approaches, which is when you try to do as much you can in both camps. Now, many people contend that AI will solve all the problems. It's the end of the scientific method, and there is many people that say no, that's not going to be like that. I am more on the second camp. I think both are important, but they are complementary. And I find this particular diagram from Dirk Helbing from ETH quite revealing, because what he showed so he's a physicist, theoretical physicist doing computational sociology. So if you think I'm crazy doing computational medicine, that's even more challenging, I think. So he has some models where he's trying to explain that as time goes by in the next few years, the processing power, we know, follows Moore's law, which is exponential, doubling every 18 months. Data is actually increasing. At the moment, it's exponentially growing and doubling every 12 months, but they say it's accelerating. There are people that talk that it will double every 12 hours in some years from now. And then the other thing he says is, well, and there is also the intrinsic complexity of the systems we are trying to understand. And those could be complexity of disease processes, because there are many interactive mechanisms, or the complexity of the system, the learning systems that we're trying to train, because they have tons of parameters. And that is modeled with a factorial equation. So you can imagine very quickly, we'll be in a position where there will be the complexity will be such that no matter how much computational power we have, we won't be able to compute the data we have. And no matter how much data we have, we won't be able to inform those models, because it will be just too complex, right? So the only way that I can think of to break this curse of, everything is actually inject priors into the whole system. And this is why you will see that there is a lot of work at the moment in techniques like, for instance, physics-informed networks, that what they try to do is incorporate knowledge priors into the deep learning techniques. So they use the learning data-driven mechanisms, but with high-level assumptions or priors that you are injecting there. I think that's actually quite a good concept, and I'm sure we will see a lot more developments in that direction. So that could be almost like a middle-out solution. So an example, for instance, of these physics-informed learnings or model-informed learning is you have a neural network that predicts certain state variables, but then you actually have the loss function, which imposes the physics that you want to be fulfilled, like like the conservation laws, for instance, you want. So imagine that you're trying to learn flow from geometry. So you put input geometry and output flow. If you don't put this term, you may match patterns but you may give certain inputs for which certain basic laws of physics will not be necessarily fulfilled, right? So that's a way to overcome that. And then a friend of mine, Andreas Meyer in Erlangen, also published a few years ago a paper where he talks about non-operators because he generalized this. They don't need to be physics operators. He used it, for instance, for projection and reconstruction algorithms. So there's geometric constraints. And he shows that actually, not surprisingly, you reduce the error bounds, right? Because you're injecting prior information. Okay, so how these all link to the things we are trying to do? Hopefully you'll see a lot of these ideas permeating throughout. Let me now explain the problem I'm trying to solve. The previous one is the story behind what I'm trying to do. And this is one of the problems I'm trying to solve, perhaps the most important one that I'm trying to solve, which is about a few years ago, a group of investigational journalists published a report called the Implant Files that demonstrated over the previous 10 years of 2008 to 2018, there was about 83,000 people who died because of devices that malfunction despite having gone through FDA and CE marking and all of the regulatory process. And about 1.7 million, this is in the US alone, that actually had serious adverse effects. And as technology becomes more complex and implants are no longer just a piece of metal you put in the hip, they are, pieces of materials with biomaterials coatings, then there is sensors on top of them that emit signal that you record and you do some AI of that. As algorithms become more and more the devices become more and more complex, then so is going to be the regulatory barriers to actually get their approval. And because the risk is high, those regulatory barriers become higher, which increases costs in the devices, time to those technologies benefit patients, and has all kind of costs, et cetera, et cetera. So we need to rethink the way, because nowadays, I mean, we hear many times about drugs, but for medical devices, they also take many years, easily 7, 8, 11 years to actually go from the concept all the way to a device that you can implant in a human. There is massive cost in trials, and this is partly what takes a lot of time as well, because it's a lot of patient collection and follow-up and look at endpoints. And in particular in the UK, we have an extra problem that this is becoming so cumbersome and so confusing, the regulation, that companies are going to the US. So you have companies in the UK pay with taxpayer money for creating innovations that first go to India to do first in humans and then to the US to get regulatory approval. So an American patient will benefit first from that technology than a British one. And by the time it comes here, we still need to do all the NHS related trials because the demographics from patients has changed as well. So if you go back and you think about the automotive industry, it's about 4 times bigger than the medical devices. It's not massively bigger. The growth rate of the medical devices is about the same as the automotive industry. If you look at the last 20 years, it's flat, meaning the amount of devices that we approve through FDA per year is flat for the last 20 years. And it's about 100 devices a year. So if you look at cars over the last 20 years, we made some progress, but not only on the product, but also on the process. We don't do any more wind tunnels. We don't do crash tests physical. I mean, you do that every now and then, but you don't need to do them all the time. You do simulations for aerodynamics, simulations for crash tests as well. We do virtual prototyping. We don't need to be always building with all the implications this has potentially as well for the environment. And we are even talking about self-driving cars, okay? So my question a few years ago is, why cannot we do the same with this other technology? So if I show you one device, and we'll talk a lot later, over the last 20 years, this device, which is a device called coils or flow diversion devices for treating cerebral aneurysms, is essentially a bunch of wires for 20 years. And we still have nearly 20% complications rate and nearly 3% mortality rate. And I say, well, you can do the same things that you do with a car. You just need to connect computational mechanics with people from imaging and other things as well. So these are the curves that I was talking. This is drugs and medical devices approval by FDA over the last 20 years. And this is the growth rate, which is 6 to 5% for drugs and devices. For the automotive industry is 5%. So how do we validate? So we go back now to the basics. What is what we need to do to get regulatory approval? They are basically, you need to provide evidence that a device is safe. That's all that the regulator is after. They don't really care whether the device is effective. That's your problem. Otherwise, you don't sell. But they care that you don't do harm, right? That's the first priority. So what we are trying to do is to say, well, there are different sources of evidence: animal testing, human testing, bench testing. Each of them has their problems. There's pros and cons. So in silico or computational methods tries to actually avoid as much as possible the need of reduce, refine, and replace where possible animal and bench testing, and also human testing, so that you only go to humans for the final pivotal trials for those innovations that you're very likely to be successful with. Okay, so you don't want to be you don't want to be going through all the animal and bench testing if you can avoid it, because it's only a model ultimately, and humans is also a model, but you only want to go to them once you know your innovations are very likely to be successful. So the challenge is, can I create models that represent that reality of humans as closely as possible, and also that try to represent, the variability of a population? One of the big differences between cars and humans is that cars, we design them for tolerance. They're all the same. But for humans, we need to design devices for resilience, so that the devices don't depend on everything we actually don't know about a human, or that is going to be varying over time or over the life course of that individual. So that's essentially what I mentioned already, but this is how the world is today: bench, animal, and human testing, a little bit of computer, primarily for bench testing. We want to go to a world where actually we do a lot less of these. We still need human testing, because that's going to be the ultimate test, the proof of the pudding. We want to go, instead of going with 20 trials, of which 15 fail, I want to go only with the 5 that are likely to be successful, right? So how does this work? Imagine, to try to pinpoint this, that we have a library of anatomical models of whatever organ you are interested in. I'm going to use aneurysms throughout my talk because it helps to focus the ideas. And for each of these aneurysms, I can implant, and I'm not sure if you see it, a stent, which I need to have models of a stent as well. But imagine we can implant them. And then we measure some metrics, some parameter that gives me the outcome measure, or a surrogate of the outcome. For instance, the reduction in flow due to the stent. So why we put the stents in the first place? We put the stents, we reduce the amount of flow that goes within the aneurysm. And you know what happens when your blood stagnates? It clots, right? So we close the aneurysm that way. So this stent in this geometry produces, what is it, the 60, a bit short-sighted, 64%, and in this other one represents 27%. The same device, 2 different patients, different performance, okay? If you do that on 10,000 of them, you will get a different performance. So you can analyze on average how it performs. But then it turns out that these aneurysms tend to break not when the guys are quiet, but when you run for a bus, when you have a change in seasonal, weather, because you cough more, or when you do some Valsalva maneuver, essentially. So you want to have models that incorporate that uncertainty that you have in the physiological regime of those patients. So what we do is we actually take from signals that were measured with wearable systems, and we generate things like Gaussian process models in this case, that allow me to know the variability across multiple subjects. So it's about 100 subjects here, but also the variability between the stress conditions and rest conditions. So I can test the devices in exercise and in rest, for instance, okay? And look at extremes cases. And of course, you can then put different devices and compare different competitors or the same device in different stages, let's say different, for instance, the strut density of the stent, right? So the way this looks like to me in my head is like a massive ensemble of simulations that need to be run, where you have one sort of macro dimension, which is anything that has to do with anatomy, mechanics, rheology, another one that has to do with the physiology, but also things like uncertainty that you have on the placement of the device by the surgeon, right? Because you never can put it exactly in the position you would want. And then on the other side, the space design. So every node here is a virtual experiment. And the challenge is how you build those virtual populations and how you build models of the intervention and the outcome. That's where, again, first touch point with all the things we do, because it's how we now can take things like UK Biobank or other massive resources that is in the UK and elsewhere to actually be able to provide analytics for instance, segmenting the vascular tree, and do that with watertight meshes in the end and proper to do CFD. So it's not just to do a diameter measurement where a lot of the geometry might not be perfect, but you get the parameter you're interested in. So in a sense, I argue it's a lot more challenging than a lot of the diagnostic things we tend to do. So let me give you now example of this put into action and some sort of examples of things that I think could be interesting. So I talked about aneurysms a bit, but let me go in a bit more detail. So aneurysms is a bulge in the vessels, particularly in the brain. They like to be usually closer to bifurcations, and they're usually close to something which is called the circle of Willis, which is a very nice circle we have in the vasculature in our brain that ensures that even if you close one of those branches, you have collateral circulation. So it's a sort of resilience, redundance mechanism we have in the brain to ensure that we have blood supply. It's not very clear why these aneurysms are generated, why they grow and why they rupture. And I'm not going to get into all of that, although we've done some work in that area. And when you need to treat, there are different alternatives. The very old ones is coiling. So this is a surgical procedure where you literally open the skull and put a clip. As you can imagine, this is quite invasive, and it takes about a month to recover from it. But then you have endovascular techniques like with coils and stents that are used as a scaffold so that the coils don't come out. And then the more recent flow diversion devices, which are stents that are very, very dense. So you don't need to put necessarily the coils, but you get still the flow redirection effect otherwise. And one of the questions is which of those you take and what combinations. That's another thing which I'm sure you've heard about cocktail drugs, right? Or combinations of drugs. And if you do a trial for one drug, now how you do a trial for a combination. Now imagine when we have cocktail devices as well. When we start putting a coil and a stent, and there is 20 types of stents and 30 types of coils, are you going to do a trial for each combination? Again, impossible, right? So examples of things where the current system just breaks down. And this is a bit the complexity of Dirk Helbing that I was talking about. This is a simple diagram of all the possible interactions of things like wall tension, the hemodynamics, the thrombosis, the wall structure, the geometry, the perianeurysmal contacts of all the different aspects that contribute to the risk of rupture of an aneurysm. And if you try to model that, fully, it's very, very complex, even if you have the data for it. So what we try to do over the past is systems that allow to do integration of all of the information. So you could see, depending on when you were in the patient's life, and given all of those parameters, what was the potential life expectancy depending on the type of therapy that you were following. And also some years ago, what we collaborated with some companies to actually develop systems that could add to the hardware of the imaging systems. These are C-arms for angiographic systems that you could add as well an element of software intelligence, which was the ability to simulate flow, because you could get good geometry from these systems, but not good hemodynamics, right? So if you take those techniques that we used in the past, but now you learn how to scale them up, and this means pretty much rewriting them, you can build pipelines like these ones that go all the way from the images to the geometries to generate tetrahedral meshes, set boundary conditions, which implies identifying inlets and outlets and specifying boundary conditions automatically, because if we want to do that on thousands of patients, we cannot do that manually. Anything can be done, nothing can be done manually. You then need to run this with some number crunching machine and maybe put some AI and physics in here. And then ultimately you get some synthetic images or virtual images that still we need to interpret and post-process. So even if a computational mechanicist sees here a simulation and see an image that needs to be post-processed. So how I quantify the phenotype of flow. So that is a number and not just a 4D spatiotemporal field, right? So if you can do that for many, many cases, you can develop, sophisticated algorithms of AI. And, in principle here is more the data than the algorithms, the challenge. But we want to go one step beyond, which is this idea of in silico trials. And for that, you need to develop essentially 3 types of things. And I'm going to give some examples of each of them, but hopefully this gives you the framework to think in your own area. First, you need to build virtual patients and virtual populations. So you need to be able to characterize and define your population. The second thing is you need to be able to do virtual interventions like putting the stent, but also virtual examinations. If I have time, I'll show at the end one example on imaging, but don't think about medical devices equates to implants. Medical devices is imaging as well. So an imaging system where you're trying to develop a new biomarker, you could use virtual patients and a model of the physics and a model of the physiology to estimate what signal you would capture if you were to actually image that patient. And then finally, what you need to have is virtual readers, which is AI again. So how to read readouts from those images or simulations or whatever, and virtual outcomes, of which I'm not going to be talking a lot, but this is how I go from things like flow reduction to death. Because in a clinical trial, my endpoints are, clinical endpoints. While in all my in silico simulations, what is easier is to do technical endpoints. So things that I can easily simulate or model, right? But you could develop models to compare one into other. So what I thought about doing is I will give you first an example of one in silico trial done without explaining how we did it. And then I'll show you bits and pieces of the tools that we use behind, okay? So this is something that took us a lot of years to get to this paper, and we're very proud of. To explain, I more or less explained this before, but when you put a flow diversion device, and we are going to be using a flow diversion device called pipeline endovascular device, or PED. This device is from Medtronic, and if you put this device in an aneurysm, what it does is disturbs the flow, reduces the blood flow, promotes a thrombus, and then the thrombus disappears, okay? And it disappears because essentially it gets sort of absorbed slowly by the rest of the tissue. So think about this what we need to model here is multiple things. We need to model the putting of the stent. We need to model the hemodynamics. We need to model the biochemistry of creating the clot. And then we need to somehow measure success of this therapy, which in that case is easy because most of neuroradiologists, what they use is radiological occlusion. So they put contrast agent after the therapy, and if they don't see contrast coming in, they say, I'm done, okay? You obstaculize the blood flow, and you take for granted the clot will come. So to give you a sense of, this paper is one of 3 studies that were done on this PED, which took 8 years from design to publication, only collected 108 pages, and it cost probably between 20 and 40 million. Okay, this device, they claim is the most well study of all of them. There are 3 decent studies, so multiply all these numbers by 3. And if you put all the patients together, you don't get to 500. So that's all the evidence with which they went to market. And to give you an idea, in Leeds alone, we put about 100 of those devices a year. So if you start putting how many they are implanted on a yearly basis, so it's not surprised that something goes wrong because you're putting in 1,000, 2,000, 3,000 patients a year, at least in the UK or Europe. And the likelihood that one of your patients will not fall within the categories of your inclusion and exclusion criteria is just easy, right? So we published this last year, and is, to the best of our knowledge, the first in silico trial that has been done where someone has compared conventional trials to in silico trials. So we didn't have the data from the real trials. I'll talk a bit more about that later, but we created a population which is indistinguishable statistically from that of the 3 trials. And we created our pipeline where we go from the images, we implant the different devices, we set boundary conditions. And here what we did is we modeled hypertension and normal tension. And then finally, the whole element of clotting as well at the end. So we created the population where we looked at parameters like neck width, diameters. And if you look at these 4 columns, the first column is our in silico trial. And the other one are the other 3 trials, POOFs, Aspire, and Premier. If you add these 3, it's not 500. But if you look at all the other quantities, they are statistically not significant, the difference, or at least within the tolerance that you do in trials. The efficacy endpoint was, the effectiveness endpoint was angiographic occlusion, which is what we did as well. And that's another thing. You need to, how you model the angiographic occlusion, you need to do a ray casting with the clotting model, estimate and solve transport equations for the bolus of contrast, and be able to model whether you would see or you wouldn't see the contrast in the first place. Okay. So what we saw is that one thing I should say is there is 88 patients in our study, but each of them we model as normotensive and hypertensive. It's like 2 patients from each of them in 2 different physiological regimes. All of the other studies mix, they don't control for hypertension. So what we observe is that the overall effectiveness is on the same range than the 3 trials. However, we also saw that when you look at only the hypertensive patients, sorry, the normotensive patients, the success rate goes higher. And when you look at hypertensive patients, the success rate goes down. Meaning that there is a parameter now that we understand how it's relating to the outcome of the particular disease, of the particular treatment. The other thing you can do with that, and I'm not going to go into the details, but is you can show for a number of elements that in the literature where there is anecdotal evidence that there are problems with the device. For instance, what happens when you have a side branch of the aneurysm? What happens with the aneurysm, with very large aneurysms that tend to not have a good clotting properties? What happens when you have hypertension? So there is only some studies that say we have problems in some of our series with these patients. So what we can do is simulate those series and create virtual patients or digital twins, you could call them as well, that fundamentally replicate those conditions. And we've been able to explain each of these 3 effects, which is something that you would never be able to do in a conventional trial, because you would either have to have a size of the study that is massive, or you will have to be able to do things to the patients that are unethical or impractical, like a stress test, for instance, right? So for instance, what happens with side branches, what we observe through the models is that, so this color coding here, that is like solid color coding up as opposed to the streamlines, is a parameter that has to do with the density of clot that is formed and the quality of the clot, while the streamlines is the flow itself. And what you can see here, this is time, clotting time, and these are different patients. So for instance, this patient and this patient is the same geometry, but this is normotensive, this is hypertensive. And what you observe is that in hypertensive patients with side branches, you get a clot into the side vessel. That implies that the whole territory that that vessel fits will be stroked. And that's where you get complications, for instance. But that doesn't happen if the patients tend to be, normotensive. So all of this is intelligence that helps you to guide the next generation of your designs as well and your devices, and what you need to take into account, what you don't need to take into account. Okay, so I'm going to focus now on some of the methods. So one thing we need to do is segmentation, and we always die to the segmentation, right? And we all try to solve that problem, but we never quite do. But the thing is, there's not just one segmentation problem. You have rotational angiography, you have magnetic resonance, time of flight, you have CTA, because depends on the pathway of the patient, you may get a different. So how you do cross-modality segmentation is a challenge, and how you do that so that you can test this on a very large cohort and it gives you high quality meshes. If you do a simple stress holding, even with rotational angiography, that is the easiest one of all of those, isotropic and high resolution, you still can miss branches. If you look to other modalities, then you have either kissing vessels that touch together or missing vessels that connect too, and all of that will change your flow. So many years ago, we did that with level sets, and to be frank, I would never go back to that, but it's a great methodology, but it just doesn't scale up, in my opinion. So more recently, we did lots of validation to just demonstrate the accuracy, but still you had to do a lot of the things manually. So we had to go from a processing over 6 weeks of 82 cases to actually try to have an automatic algorithm that takes 30 minutes per case and is fully automatic. So things that we are developing is based on machine learning. Again, examples where the data-driven approaches are good is for segmentation, but we don't only segment, we do the segmentation, we detect the aneurysm, we compute center lines, we detect the endpoints, we detect the point where we need to release the stent, and then we need to do mesh generation from that. So all of those steps are automated. And we've done quite a lot of comparisons with other techniques. The other thing which is interesting is if you work in angiography, most of the people give you a segmentation of the region of interest of the aneurysm, but you want the whole vascular tree. So we develop techniques that you only base on one part, you only have ground truths in one part, but you can scale up to segment the rest of the vasculature that works fairly good, like this example. So this is the region of interest, and this is the segmentation we obtain at the end. Now, the other thing that is important, just to give you examples of things that seem simple for us, but is actually a nightmare when you want to automate, like in which vessel is the aneurysm, right? Unless you have a spreadsheet that tells you that, and if you want to automatically infer this from the images, what you need to do is something of this sort, which is you develop a graph of all the circle of Willis with all the different vessels being labeled, and then you need to find a mapping between the graph of your aneurysm or your patient to that template graph, and then you inherit the labels from it, right? Now, there is a problem. The reason, well, we did that with some techniques, but the challenge is there isn't just one graph that is physiologically correct, anatomically correct. There is like 13 variants of the circle of Willis, which some missing vessels which are not there when you're born, but you're okay. So you need to find, it's a multiple model problem matching, where you need to identify from all the possible subgraphs, the models, which is the one that represents your patient, and then do the labeling accordingly as well. So the colors here represents labels, and in that way we can automate, for instance, assigning boundary conditions. Because if I know it's in this particular segment, I know what vessels I need to take as inputs and as an outputs. Another issue that is important as well. Many of you will know that when you do a trial, there is inclusion and exclusion criteria, and that puts a bias, a selection bias. And that selection bias is controlled, hopefully, because you want that to include and exclude certain things. But sometimes there are also biases that you can't. There are recruitment biases that you cannot control, like how many patients will come. UK Biobank, which we all are very happy with, has a major problem that is only 9% of the people that were invited to participate actually say yes. So you can imagine that there is a massive bias to who actually went through UK Biobank and who was imaged or was taking any of the pictures. It's people who are well off, who can spend 5 hours doing all the examinations, who can drive to the place where they do the imaging. It's not everybody. It's a very specific subset. Anyway, it's the best thing we have in many cases. So another problem, UK Biobank doesn't bring you brain vasculature. It has brain imaging. It has T1, T2, proton density, it has a number of those, but it doesn't have MRA. So if you want to use, say, the 40,000 or 50,000 subjects that are now from UK Biobank to create vascular trees, to do in silico trials at that scale, you need to do something. So what we developed is a technique that actually allows to take the 3 images that we have available in UK Biobank and is able to produce synthetically angiographic images. And this is done by learning the mapping in another population where we have both modalities, and then basically apply that to UK Biobank. So what we show is that you can do that with quite a good accuracy, and we compare a number of techniques to do that. And I'm going to ask you to do a Turing test with you, which is, can you tell me which of these two is the real one, and which one is the synthetic one? So what I'm doing now is a maximum intensity projection, where I'm going to the back, and then I'm doing a slab maximum intensity projection, so you see the vessels coming in. So one of these is real, the other one is not. I can tell you it's not easy, but so this is, well, it's another type of projection. So that's a synthetic one, okay? So what we developed is a way to actually compare now the synthesized geometries with the real ones in the database we had, and look at what is the influence of the synthetic case in things like the fluid dynamics that we want to simulate downstream. Do we have the same size, the same geometry? Does it change our wall shear stresses, right? So all that work has been done as well to do comparison. I think there's going to be a lot of work into how we generate data that is not available from other data sets. And there is all kind of interesting problems there as well for us. I'm going to skip quite a bit. So one of the things we did that I'm not going to go through that is we did a lot of sensitivity analysis to show that actually our simulations to what it was depending. We also developed ways to quantify the flow in an automatic way, because if I give you just simulations like this and I tell you, tell me how this flow differentiates from that, is very complicated. These are time sequences in 4D, in 3D of vector quantities, right? So that you can then utilize those metrics to do things like, you know, what sort of type of flow pattern correlates more with rupture or less with rupture. And start looking at what sort of type of patients are less likely to have problems or more likely to have problems. You also need to develop models of the stenting itself and or any therapy that you want. So that actually is, again, we have a lot of expertise in our community, because at least some of us that are old enough, we come from deformable models and from simplex meshes and all that stuff. And you can use some of those techniques to accelerate things like deployments of stents. So this is a it uses some heuristics, but it's not a full computational mechanics solution, right? However, we have shown through simulations or experimental simulations and finite elements that this fast virtual stenting that takes about a minute to deploy, while this one takes, you know, a fully coupled mechanics deployment of the stent can take several hours. And in most cases, it doesn't converge when you put it in realistic geometries. If you look at many papers from people who do these models, they do it in nice and sweet sort of vessels, which don't exist. But when you put them in these complicated, tortuous vessel trees, they just diverge. And then you can do comparisons between virtual and real experiments where you can actually show how the flow patterns. So remove the blue one, which is basically a measurement in here. The other two curves, the pink and the green, are two measures inside the aneurysm. They show complete overlap between the time dilution curves of the aneurysm virtually deployed and the experiments in terms of injecting a contrast agent and looking at the time dilution curves of those. Okay. The other type of devices that you want to model, and is complicated, is actually coils. The problem with the coils is that they are kind of a stochastic, right? So how do you put them? You know, what do you plan? So, and there is tons of types of them. So what we develop is a technique that captures the most important features. So what you try to do is you try to put these coils, remember, you're putting these coils through femoral access. So you go through the groin all the way with a catheter. You don't see the aneurysm, you don't see anything. It's all under fluoroscopy. So you put all these coils, and what these guys do is they start filling the aneurysm to a point that it reduces the flow, right? That point, that filling rate, is measured as the volume of metal you put over the volume of the aneurysm. And that's a typical clinical parameter that clinicians use. And this is how it looks when you do a surgical specimen or a histology specimen. You see all the struts there. It's a mess. So how you model that process? So what we develop is a sort of technique that is based on a minimum cost path type of approach that has some heuristics. So it cannot self-intersect. It cannot go, 90 degrees. It cannot go through the vessel wall. So it has a number of practical rules into that. And we can actually insert those, and each of those colors is a different coil. It's about 1,000 pounds each of them. You put between 6 and 20 of them. So you can imagine 2 or 3 less or more is a lot of money. So what do we model here? So imagine that these coils are a random field, okay? So the first column, the first row, second row, or third row are 3 realizations of the random field. I put the coils, I take them out, I pull them again, I take them out, because it's a stochastic. The point where I enter is not always the same. They're going to end up in different positions, like a clinician, right? But the only thing I keep fixed in each of these realizations is the packing rate, the 20%, 25%, 30%, because that's the only parameter I can control. how many coils are put. So what we observe is that as you increase the number of packing rates, surprise, surprise, it doesn't matter anymore how many of them, how you put them, sorry, exactly. And the flow arrives to an asymptotic value of maximum of amount of flow that manages to get through, supposedly through the porosity that is residual to that mesh you put. So this was published in about 10 years ago, back in 2013, 11, we did this work. 10 years before that, in 2002, we found a paper that showed that aneurysms that were stable, meaning they didn't reopen, or unstable, they reoccur, they tend to be larger in packing rate than the other ones. The packing rate was higher. But also that this packing rate that was higher was different depending whether the aneurysm was small, large, small neck, wide neck. So this is a mini trial, you could argue, that actually we replicated 10 years later without knowing, but now we know something else. We can define, we know that it's not just that the bigger ones and the smaller one, there is an optimal value for every patient. We know for sure, we can tell you now for a particular patient, beyond which you don't need to put coils anymore because it doesn't make any difference to the flow. The only thing you can do is overpressurize and burst it. If you put less than you should, then it doesn't close completely and you may have a reopening, a recanalization, right? So again, perhaps we have been during 10 years improving devices when the only thing we needed to know is how many we need to put instead of changing the device, right? I'm going to skip how we validated that with animal models. And this part perhaps is less interesting from an imaging point of view, but you also need to do some signal processing on wearable devices to actually model these physiological regimes and model different levels of stress for different types of patients. And I'm going to skip the part of the plot. So let me just go to the conclusions. So the three things that we said before, virtual populations, and now I put below a lot of topics which are related to us that actually link our work with some of those. We need to develop these virtual populations. I mean, a virtual patient doesn't mean the whole body. As I showed you before, it's just the aneurysm in this case. But for some applications like imaging, you might want a torso model. And in fact, the US, for instance, has in FDA, they have done an in silico trial of an imaging system where they use these sort of complex torso models to look at breast tomosynthesis and their advantage over conventional imaging. So there are people doing, I think we need to, our community, we need to go, I think, to become more engineers of biomarkers as opposed of fishing expeditions for biomarkers, if you see what I mean. Rather than compute things and see what correlates, what we need to try is to understand the mechanisms, model them, the physics, model the process, and somehow try to then almost design a readout that will give us the right type of information by construction rather than by being lucky, right? And I think for too many years, we've been trying a lot in this area. So digital twins and virtual chimeras. So digital twins or virtual twins, if you are a bit into that jargon, is a digital replica of a physical entity where there is a real-time connection between the two. In patients, most of the times it's not true. There is no real-time connection. But kind of, we call it digital patients anyway. But the other thing is that sometimes, well, I think most of the times, at least to me, has happened that when I want to build one of those models, I can never get all the data from a single source. I can have a database where, like UK Biobank, where there's massive information on geometry, but they didn't have any invasive measurements because that's a volunteers study. And you have another database where they did wearable devices and they have physiological regimes, but they don't have imaging. So what you end up having is data sets which are isolated, each of them, and you need to blend them. And this is what in statistics, some people call them data sets of data sets, right? And how you do generative models that are able to generate populations based from each of the marginals effectively, and to build the joint distribution, I think is a very interesting problem as well, especially when you work with very high dimensional, very complex structures. Some of the things are meshes, some of the things are, categorical values. Because only when we do that, we will have the ability to spread to explore the experimental space in a full manner. Otherwise, what we are doing is just mirroring the trial. And this is useful for validation purposes, but I don't think is the practical way forward. So that's why we call them virtual chimeras, because they are not one real patient and a mixture of stuff, right? This incidentally solves the problems of information governance as well, solves a number of other issues on the way, because no, you cannot trace to any particular individual. So in summary, I think, you know, you've seen in the conference, and I'm sure and in other conferences as well, that AI is doing lots of advantages in detection, classification, automating essentially tasks which are subjective. I think what we are trying to suggest is that there is a possibility to go beyond that, incorporating both priors, either that can be inferred from the data itself or through mechanisms. I think these models also give you a way to do fusion, which I was saying, when you combine multiple modalities and then you simulate. That simulation incorporates all the inputs as well, in not just geometric way, but in a sort of a epistemic way, essentially, because you're bringing all the different mechanisms together. Well, I think I mentioned the importance of full automation, and hopefully I injected an idea or two that might spark in you the interest to work in this space where there is a big need. And thanks for your attention.
So thank you very much, Alex, for your fantastic talk. So there are tremendous work, and also this is conference called Medical Image Understanding and Analysis, but you're obviously going to the next level already. So any questions from the audience?
Thanks so much for speaking. Can we go back to the slides where they made the MR angiography from the T1, T2 and proton density? Sorry.
This one or the next one?
Either is fine.
Yeah.
That was crazy. So I was just wondering, first of all, with the MRA, does it just tell you the position of the blood vessels, or does it tell you like flow through them?
Well, what we did was just essentially generate an MRA from 3 contrast and enhanced imaging. And there is, by the way, something I should have mentioned, there is work by, maybe Carola, you can help me, you may know his name. It's a Korean guy, Jeon-Chul Ji, is it? That he has a paper in one of the Nature journals, Machine Intelligence or Computational Sciences, where I think he demonstrates in there that any endogenous contrast agent, any endogenous contrast in MR could be synthesized in this way. So if you wanted contrast enhanced, I wouldn't be able to do it. But I think that the reason why it is possible is because we are synthesizing time of flight effectively.
Okay, so if I was
there's no flow.
Okay.
Your question. However, I think you could do that as well. If you had phase contrast, a data set where you have this and phase contrast, we could train a network to do that. And you can do it with physics-informed network to enforce all the equations of flow that need to be conserved on the other side as well, if you have a data set large enough.
Okay, so that could save like loads of MRI time then.
Potentially.
That's really cool. Thank you.
You might have answered this. I wasn't sure if I caught it, but so every year we see all these new AI and new techniques, and as far as I'm aware, it's actually still quite difficult to convince health providers and governments to actually buy in, even though every year we see more and more impressive results. Is in silico trial, you convince me, but is it convincing the regulators? Like,
the right people to convince in silico trials is the regulators, because they're the ones who set the rules.
Yeah.
And then they mobilize industry, and then the rest follows, right? So I could give you, well, if you are interested to follow all this story, there is, if you go to insilicouk.org, There is a community of people that I'm sort of, one of the things they expect from us in the Royal Academy of Engineering is that we champion the discipline we work on. So I created a community. There is a web page, but there is also a Slack, which has 1,200 people already. A large number of those come from MHRA, from FDA, and from EMA. And I could point you to documents from FDA in particular. FDA is running with this. I think they're coming from the point that it's just unsustainable. I mean, the cost we are incurring in healthcare because of trying to do it in a, look, I mean, a conventional trial is a glorified trial and an error approach. We don't do airplanes that way, right? We don't do cars that way. When we do the most delicate part of our healthcare, we still are doing it. I do think there is a sense that you always will have to do a final trial, but the idea is that if you could, through an in silico approach, you know the magnitude of the effect you want to measure. You might also be sizing the trial more accurately and more narrow, so you only get as many as you really need to put at risk. Because those people, you're putting them at risk initially, right? Before you demonstrate is a good thing.
Has there yet been an example of an in silico trial that was the regulator, maybe not somewhere annoying like the UK, accepted?
Yes, so at the moment are more ancillary type of things, but for instance, Medtronic got approval for leads for a Parkinson device. That those leads were, they provided all the experiments, but they also provided experiments about heating effect of the leads, and go and try to do a trial of that, right? So what they did is they validated the model of heating in animals, and then they did all kind of permutation tests about possible configurations of the leads, and they demonstrated on 1 million of those configurations that there was no heating impact potentially. And the person from Medtronic that was telling me this was saying, we never have implanted 1 million devices yet, so they wouldn't even have had the possibility to test it in a real trial.
So time-wise, we may have one more question, please.
Thank you, Alex, for a fantastic talk as usual. I have a couple of quick questions. So first of all, how do you validate the results of in silico trials? I mean, with the real clinical trials, and especially complex diseases such as cancer, which is going to be my next question, that for those complex diseases where we have lots of different molecular pathways and genetic and epigenetic changes involved, we don't really have models of disease biology and physiology and treatment responses and biochemical phenomena. How do we go about in silico cancer trials? Your thoughts on that?
So I'm not into, well, the only aspect that I'm thinking already for some time in relation to cancer is the application of this for radiotherapy strategies, because that's another thing you can do trials of. This is not a device, but it's an approach, like how you fractionate, how you put your rays, how you design your your radiation systems. For those, I can figure that out. I come more from the devices. I don't have a clue how to do this in drugs, although I know people do that as well. I would say first question is how to validate. Well, one of the things that the way I think you will use these trials is with chimera trials, those that you compose populations by blending multiple subjects. But that is not good for validation purposes because it's too mixing things. For validation, I think you need to do twin trials. And at the moment, we had a couple of companies that have actually provided us access to the whole data set from devices that they took off the market. So one device I'm thinking of, this is a story, it's a sad story to hear the impact of all of this. We have now the full data set, it's about 20 terabytes with all the imaging, all the biomarkers, everything from about 1,000 patients from a study of a cardiovascular device. That cardiovascular device cost 80 million to generate that data set. That was the cost of the trial. The device was recalled from the market in November 2020. It cost between 200 and 300 millions in losses to the company, right? And they were going to be throwing the data set, so please give it to us, right? So we strike a deal with them, and we now have a data set where we know the outcomes, we know everything. So what we are trying to do, and I hope in a year's time I may be able to show that the results, because it's not in the brain, it's in the heart, so it's a completely different story. But what we want to do is demonstrate that we can predict at the patient level the response, and then at the group level, because what we have done is show at the group level, right? So what I think we need is about 10 to 12 of those comparisons being done, and ours is not the only one. Now there is a recent paper from a group in Bath that did an MSK device. There's a mounting evidence that is coming up that this, at least in certain devices, is possible. I frankly don't know how you would apply this to cancer. But what I would challenge you is, shouldn't we perhaps spend more money in understanding the disease and modeling it rather than in developing drugs and things, which is where we don't have that expertise? Because if we actually don't have that understanding, what are we doing? What are we doing trying to treat that? So perhaps this is a bit of a more humbling point, in the sense that what it tells us is you need to model to understand so that you can optimize. And maybe this is not possible in certain areas yet, because the knowledge needs to develop. That's perhaps why I chose cardiovascular and devices and not other things. But that would be my challenge back. If we don't understand enough, what are we doing? What are we doing? You know, what are we doing with imaging, for instance? What are we looking at?
I mean, people who are running those trials will probably say in their defense that you can't wait until you understand everything completely while you're, trying to tackle the disease. And you have to run some sort of trials, treatment 1 versus treatment 2, and see which one is more safe and effective. So that's what they would say. But I'm with you that we need to understand.
And that there is a balance, how much we try to solve without understanding and how much we understand without solving, right? There is a balance between these two. But I think what I like of this approach, it forces to declare your assumptions, right? It's a white box. Well, there are some black parts like the image segmentation and all of that, but it forces you to declare your assumptions. And a conventional trial has tons of assumptions as well. They are undeclared or declare only if you understand what you're an epidemiologist, what a trial is. Anyway, I think you have a point. There is very complex diseases that we don't fully understand to do this, and maybe that's not the right approach for those.
Well, I think that's the end of this session. So let's thank Alex for this fantastic keynote.
Hello, Caroline.
I hope we can catch up later, maybe,
Yeah.
but it was great.
Thanks a lot.
Does this work? Wang? Do we need to do something? It doesn't seem to be working. I meant, oh, there we go. Yep. Okay, so just before we break for lunch, we've now got 2 flash talks from our industry sponsors. So first we'll start with Javier from Microsoft.
Hello, everyone. I'm going to be very brief because I think we are all ready for lunch. I'm Javier. I lead the biomedical imaging team at Microsoft Health Futures, and we are sponsoring this conference, and I'm super excited to be here with you today. I would like to thank the organizers for giving me this opportunity to talk to you about the work that we do and how we are contributing to the conference. So in the biomedical imaging team, we are focusing our work on these 4 quadrants. We are working on radiology, pathology, and we are trying to assist and augment clinicians with writing reports. And we also focus on multimodal learning as a key area to create foundational models that can be scaled to many different tasks and applications. And we work with partners to get access to real-world problems and data sets. And we open source all our code to democratize access to medical imaging AI. So the biomedical imaging team is part of a bigger organization called Microsoft Health Futures. But our team is based here in Cambridge by the train station. You can see our building here at the top. And Microsoft Health Futures is focused on empowering every person on the planet to live a healthier future. And we are a diverse group of researchers, engineers, scientists, and medical professionals that focus on end-to-end research projects across healthcare and life sciences. And we have a diverse portfolio of projects around imaging, NLP, signal processing, genomics, and immunomics. Now I would like to show you a video about a project that we have done in the past with Addenbrooke's Hospital here in Cambridge. This project is now deployed clinically in the hospital and is being used by clinicians. In this project, we try to accelerate radiotherapy treatment with machine learning. And we've managed to go from taking hours to do the work to plan radiotherapy to 5 minutes. So I'm going to show you this video from one of our collaborators in Addenbrooke's.
When I decided to become a doctor, I didn't realize that artificial intelligence will play such a big part in my life. My name is Raj Jenner. I look after patients with cancers of the brain and spine. We do this by using precise radiotherapy treatment to kill off the tumors and save lives. Planning radiotherapy treatment takes many hours, carefully marking up scans in order to direct the radiation to the tumor whilst shielding healthy structures around the tumor itself. So my team at Addenbrooke's Hospital and the University of Cambridge have been collaborating with Microsoft Research to train computers to perform this task more quickly. The results are incredibly exciting. The research, known as Project INRAI, have shown that a computer can perform in just a few minutes what would normally take me several hours to do. This is important because it means we can start a patient on life-saving radiotherapy much more quickly. And we know that the sooner that we can start treatment, the better the chances for the patient. The deep learning software tools from Project INRAI have now been released as open source code. And we look forward to using these tools routinely to speed up the time taken for patients to start radiotherapy treatment here at Addenbrooke. Using AI to help doctors with complex but routine tasks is an absolute game changer. It gives back clinicians the gift of time, and it means that we can focus on the parts that only humans can do, which is actually caring for our patients. When I decided to become a doctor,
Sorry. So yeah, if you want to learn more about the work that we do, come to our booth. We are also running a workshop this afternoon at 4:30. So we are going to talk more about the open source work, the multimodal learning research, and our computational pathology pipeline. We will be tomorrow as well in the industrial panel and in the closing ceremony and awards. And if you are interested in internships, please watch out this URL. We will be posting the job ad for internships next year in September. And finally, I just want to leave you with these tweets from Satya Nadella, where he highlights the importance of AI in healthcare and the urgency to apply our research to the real world. Thank you.
Hello. Okay, thanks a lot for that. And we now move on to Euphoria. Feel free to start.
When does that start? Okay, well, I'll be really quick. I know I'm the only thing between you and the lunch. So, well, Euphoria is not a very big company. It's a small company, around 100 people. We are from Finland. but now we are in a few other countries as well, including UK. I will try and skip all of my slides, to be very frank. Workflows, I'm not going to talk about neural networks. It's going to take too much of time. Again, some marketing stuff. I think I'll just switch to the software itself. We provide imaging solutions, image analysis solutions. In short, what you're seeing over here is a blood sample from a patient which is affected by malaria. Yeah, I don't know if you can see. At some point, you're going to see blood cells with positive malaria infections. These ring-like structures are malarial parasites. Yeah. Idea in this case is to automatically determine all the counts. It's a cytology work. And this kind of algorithm most likely takes, in this kind of a platform, around 30 minutes to make itself. Analysis itself took 35 seconds for this. Yeah, cloud computing makes it faster. Another solution, which is soon also telling you a little bit robustness on how cancer epithelium is being detected, counting of the nuclei is happening, and also high quality tissue. Yeah, often in the analysis, you want to avoid things like folds. You want to avoid things like autofocused areas, defocused areas. But at the same time, you want to get your whole data to be analyzed as soon as possible. Yeah. Switching brain, talking about neural networks. Again, this is a pretty complicated model, but it takes a little bit of time. So different parts of the brain, so all of these models that I'm showing you are not made by us. It's made by our customers. They are annotating. You don't need to know coding. And they are mostly doctors or researchers. Yeah. And again, you need a little bit of training data set, click a button, and you get your analysis out. It can be anything. This is a bit of a challenging case. It's a pretty big sample, but I'm just going to load data for a small area. It's a mouse brain, again. Microglia cell, again, talking a little bit about instant segmentation, because we have had a nice lecture also today morning talking about instant segmentation. So here in this case, we are looking at detection of these individual cells, true microglia cells, and then also looking at all these processes coming out. You see these pink dots are all the individual processes coming out. To complicate it even further, you can also look at the instance of all those individual neurites that's coming out of the cell. Yeah, I don't want to go too much into detail, but this piece of module can also understand overlapping areas of two biological ground truths. We are talking about CE-IVD marking. It's very difficult to get the CE-IVD marked products for software. Professor Angelo already mentioned about that. But also to tell you a little bit about, this is CE-IVD marked product, not only the algorithm that you're looking at over here, but also the, so this is a small mitotic cell. I don't know if you can see it clearly, hopefully now. It's literally a needle in a haystack situation. It should align soon. Okay, there. And on the bottom, there are the rest of the markers for, Ki67, PR, PR, all CE-IVD marked at this point of time. It's very difficult. It's super expensive. So we try our best to also give this out to customers in as cheap rate as possible. Again, people sometimes don't even accept this because it's very new for them to accept such a technology. Yeah, I think I have prostate cancer. It's one of the nightmares for pathologists to understand what is the grade of the cancer. Yeah, this is also now possible with the software that we have also CE-IVD marked at this point of time. We're going next. This is, again, literally my last slide right now, to a retrospective study. Not only to grade the cancer, but also to predict survival of how that cancer is going to go in the future after surgery, for example. Yeah. So it would help for one to understand either to include or not to include therapy for that patient. Some of our customers, Cambridge is one of our customers. So it's nice to see that it's already being used in the university. And also Mayo Clinic, we are thankful for Mayo Clinic for selecting iPhoria for using it in their clinical and research workflow. So it's one customer that we are allowed to talk about. Yeah, I don't know, that's pretty much it. We have been acknowledged by some well-known magazines as well in the past. So yeah, visit our booth if you have any questions, if you want some sort of a collaboration, feel free. Let's go for lunch.
everyone.
Yeah, we just have an announcement that, you want to?
So hi, everyone. For the next poster session is the largest one that we have so please